So, good morning, everyone. I'm very pleased to be here to present you the vulnerabilities I have identified during a security assessment project of hardware wallets, OneKey. These vulnerabilities are primarily a result of a poor understanding and consequently a misuse of the hardware components embedded on the wallet. So, who we are, I'm Mouchous. I work at the dungeon the product security team of Ledger. Ledger has been producing hardware wallets since 2014, and the dungeon was created to assess and enhance the security level of our products, but also for all of those of the cryptocurrency ecosystem to enhance the security level of the whole ecosystem. So this study was performed with my colleague Karim, who is here, along with the support of Olivier Rivaud. I would like to greet and thank them, as well as all the other people at Ledger. So, the context of the evaluation, it has been conducted last year in 2022, in the context of creating a mid-cost laser fault injection test bench. In order to validate the operation of the test bench, the OneKey Mini was the ideal candidate because it used a secure memory to store confidential values. This memory is ATECC-608E, and it has been evaluated by Olivier in 2020. And the study he made revealed that the ATECC is vulnerable to laser fault injection attacks. It also embeds MicroController Unit, the STM32, which has been attacked by Karim previously to dump the internal memory of the MCU. Reproducing this attack will permit us to prove to be useful during the study to get some values that enable the communication with the ATECC, and then to diagnose when we perform the laser attacks for data corruption activities. And lastly, the project is open source. It's based on the Trezor project, which is also known by our lab, with the addition of the secure memory, the ATECC-608A. So the presentation I propose will begin on the hardware description of the architecture of the OneKey Mini. Then I will present three kinds of vulnerabilities based on the misuse of the ATECC. The first one was revealed when we dumped the memory of the MCU. The second one was an improper configuration of the ATECC for the pin handling of the hardware wallets. And then I will showcase the laser fault injection setup and the campaign, which will give us a third weakness based on the choice of the hardware. And finally, I will recap all of the vulnerabilities, give some takeaways, and a word on the disclosure. So first, the hardware description. The hardware architecture of the OneKey Mini is quite simple. There is a MCU at the center, which runs the firmware. It controls the inputs and output functionalities depicted in yellow at the top of the diagram. There is also a flash memory on the left side, which stores some extra data, so some images, NFTs, and it is also used for the updates of the firmware, but it's not that critical. And the most critical data are stored in the ATECC, which is in orange on the right side. So it stores the seed of the user and the pin, the hash value of the pin. So we will focus on the two components, which are the MCU and the secure memory. So the ATECC is a secure authentication IC developed by Microchip. It has three revisions, which can be available on the market: the 508A, the 608A, and the 608E. On the vendor's website, the 608A and the 508A are noted as deprecated. So the constructor should not use them anymore for more than 1 year. The ATECC has some security features. Not all of them are used by the OneKey Mini. And we can say also that, unfortunately, the OneKey team has not chosen to upgrade to the 608B. The 608B version has a lot of security improvements about some attacks that will be presented afterwards. So the memory in the ATECC operates through slots. So there is 16 slots which have a variable size, but here are used as 32 bytes entries. They can store keys, certificates, or user data, and each of them have protection levels, which are set during the configuration, the initialization phase, and the configuration of these slots is immutable after the initialization phase and cannot be changed the whole lifespan of the ATECC. The slots content can also optionally be immutable to make the data to be completely locked. So here's a table presenting the different protection level, which can be set independently for read or write operation. So there are three of them. First of them is public, where the command can be openly done, and data can be read out or written. The second one is protected, so you reference another slots where you have to give during the read operation with the gendic command. You specify the slot containing the key. With this command, the ATECC on its side computes a temporary key based on the SHA and the value of the key contained in the key ID slot. And then it grants access to the read or the write operation by exchanging the data with a XOR operation with the data. So basically, if you don't know the content of the key ID slots, you cannot manipulate the data of the protected slots. And the third protection level is private, where the read and write operation are always refused after the initialization phase. So you initialize your ATECC with the data contained in this slot, you mark it as private, and then the value contained in that is totally locked. There is also a flag that you can set for a slot, which is e-secret. This flag permits to activate an internal encryption of the data with an AES, and also the security level must be at least protected. So here is a table of the configuration of the OneKey Mini. So there are 9 slots used, and the two we are focused on is the user secret, which contains the seed. So it's 24 words that the user have to keep secret to grant access to the funds on the blockchains. So the other slots on these 9 are set as public and non-secret. So the slot number 6 is marked as protected with the slot number 1. So it means that you need to know the data contained in the slot number 1 called the IO protect key in order to manipulate the seed mnemonic. So when you want to make a transaction, you perform the read operation on the mnemonics and then you can make a transaction. So you can see that the IO protect key is set as private. So it means that you have to store it outside of the ATECC and keep it secret. Also, we can notice that the slot number 6 is marked as secret, meaning that when you want to manipulate the data, there is some AES. So on the MCO side, in order to store the IO protect key, the OTP memory is used. So the OTP memory is a one-time programming memory, which is 16 blocks of 32 bytes. The initial value is FFFF, and it's fused writing, meaning that the bits can set from 1 to 0. And after the writing, you lock each block you have written, and to get them immutable. So this is how the OneKey Mini use the OTP memory. And when you are securing your MCU, the STM, you are at a security level where you cannot run the bootloader in order to change the value of the OTP. So only the firmware running on the MCU can read the OTP. So here is a table presenting the OTP layout and the purpose of each used block. So we can see that the block number 9, there is the value of the IO protect key. So when the MCU wants to read the seed, it read out the contents of the OTP memory at this block and proceed on the reading of the seed on the ATECC. So we can see that on the last column during the initial phase that this slot is initialized by generating a random from the ATECC as the initialization phase. And we can see some other blocks that there can be some hard-coded value, such as the slot number 13 or other ones. So the first vulnerability I will present has been outlined when we perform the OTP dump of the MCU. So the attack description of the goal of the attack is to retrieve the value of the IO protect key from the OTP. So the method was to inject a perturbation during the boot process in order to grant access to the bootloader and then get access to the OTP by reducing the protection level in order to read out the memory. So this attack has been performed several times on several versions of the STM32 by Karim, and it has been done successfully again. And the main point is that when you have access to the bootloader and you want to get access to the OTP, you have to erase all the contents of the flash memory. That is not a problem because the IO protect key is stored on the OTP, so the attack is easy. So here is a setup of the protection bench. So you have the silicon toaster, which is our EM injection probe developed by the Dungeon. Just below you have the MCU, where the firmware is running and it's controlled by the scaffold board, which is also developed by the Dungeon. So the scaffold is used to make the communication with the MCU, to give some signals to trigger the silicon toaster, and then to get the measurement of the currents that you can see on the right side of the slide. So the silicon toaster is a EMFA probe. It's a bank of capacitors where a coil where in it an antenna coil has a high current injected in it in order to perturb the boot process. So you can see on the right side the boot sequence without the perturbation in blue, and the perturbed boot sequence on the top on the red curve. So here is the result of the MCU OTP dump we got on the one first key. So we can see that some slots, like the 13, has a value that are expected. Also the slot number 8 and the unused slots, which are still at FFFF. But something which is quite surprising is that the IO protect key has a very fixed pattern, which is FFFF 000, FFFF 00. So we can assume that we had a problem during the extraction of the data, or we have get some data corruption or things like this, or countermeasure from the MCU which erase complexities or random data. But actually this is not possible because for the data corruption, the range of the data corrupted is very specific and not that random. Also, the value are not random, and it's not an action from the MCU because, as we have seen before, the OTP is a fuzz writing, so it cannot. You can only set the bits to 0. So if the MCU wanted to erase the key, you will have written only zeros. So how is it possible? We don't know yet. We tried this key on the ATECC in order to check if the value is the actual one. It's the one also stored in the slot number 1. So there is 2 ways to do that on the ATECC. There is a checkmark command where you compute the mark of the slot number 1. You give it to the ATECC, and it responds you okay if the mark corresponds to the content in the slot number 1. The second way is to read out the value of the seed. So you generate the temporary key. You perform the read operation at slot number 6, and actually you get the value of the seed that has been provisioned during the initialization of the OneKey. So actually, the OneKey has a static key which is FFFF000, and this value is contained in the slot number 1. This vulnerability, I would say, is that the value is not random, and it's impossible to patch because, as we have seen, slot number 1 is locked, and the OTP is also locked. So on both sides of the hardware, there is no possibility to patch. So we wanted to confirm this attack, this vulnerability, and we tried to dump the memory of the MCU on the second one. So we bought another one in July, and we performed the OTP dump once again. And now we can see that the value are random, also for the slot number 10 and 11. So 2 questions arise. Is the first one, why the first version of the OneKey Mini has a non-random key, and why the second one has this random value and has a different behavior from the first one? So we dig out on the initialization phase of the OneKey Mini. So basically, during the initialization, the first boot up of the OneKey, the MCU initialize his OTP by performing some random commands on the ATECC to get random values. It stores the values to the OTP, and then it performs the initialization of the ATECC by writing the configuration we have seen before, and writing also the data of the slot and lock the configuration and the data zone. And from this step, all of the initial phase of the MCU and the ATECC is done and totally. And then we dig out on the datasheet of the ATECC, and we found something very interesting about the random command. And we have found that prior the configuration zone being locked for testing easing the testing of the ATECC, the RNG produce a fixed value which is FFFF000. So we have found the source of the first question, which say that because of they are performing some random commands before locking the configuration zone, all the OneKeys which perform this operation have the same key. And then we dig out to find the response of the second question by browsing on the GitHub. So we try to see when the change of the configuration, the initialization function, is effective about the behavior. So we have seen that there is a change at main 9 where the configuration zone is locked prior the random command calling. On the commit message, there is no specific thing about patching a security issue or thing like this. So there is no specific details about what is the purpose of the change. But it occurs on May 9, 2022. And then we wanted to dig out about the difference between the two wallets. So we looked at the MCU serial number of the two wallets, and we have seen that the first one has a date which is 2021 of December of this year. So it's before the code change. And the second one has a date written in the serial number, which is May 18, 2022, so 9 days after the commit. So bad luck for us. We didn't get a second OneKey with the same non-random key. But we have found a second the answer of second question. So the second vulnerability is about the misuse of the ATECC, is about the pin handling. So what is pin handling, the pin code for the hardware wallet? So the purpose of the pin is to prevent the hardware to access to the seed without for the user without entering his pin code. So basically there can be some restriction to the reading of the seed by either encrypting the value of the seed with the value of the pin code, but this can be brute forced offline. But also, if you have a secure element, you can grant the access to the data containing the seed by proving that you know the pin code. So how it is done on the OneKey Mini? So it's this is the execution of the MCU. So the MCU prompts the user for the pin code. It verifies by the checkmark operation on the hash value stored in the ATECC. The ATECC say okay or not, and depending on this response, the process continues, and the MCU readouts the seed slots as we have done before. But before we didn't enter the pin, so actually you can begin the process from this point, and the pin code is actually ineffective. So why the authentication chip doesn't use the pin code? Actually, it's a feature proposed by the ATECC, and it is something which has been not well configured by OneKey Mini. So the feature is called password checking. So you have to prove that you know the value of the content of one slot in order to get access to a second slot which contains a second high entropy secret. So the configuration of the OneKey is done on the fact that we have to prove that we know the value of the slot number 1 in order to access to the slot number 6, but this feature should have been configured as to prove that you know the value of the slot number 2 instead of the slot number 1. So this change of configuration is also impossible to patch for all the OneKey present on the field, because the configuration zone is locked on the ATECC and can never be changed. So the third vulnerability is based on the laser perturbation campaign we have done. So basically, we didn't have started to perform laser attacks, and we will see during this campaign that the use of the hardware is still a vulnerability for the OneKey. So the laser fault injection bench I created is a mid-cost laser bench. So it just have on-the-shelf laser diode developed by Alphanov, a very basic set of optics where there is just a collimator and a lens, and a regular camera used to approximate the positioning of the laser beam, which is done with a low-priced actuator. For the preparation of the ATECC, a very simple preparation has been done by milling the ATECC to remove the plastic and the little slice of copper. There is no need to polish or thin the chip to get perturbation, which were effective. So here is the configuration of the ATECC we got. So we bought some open sample to perform fault injection attacks of both revision of the ATECC, the 608A and the 608B. We have the similar configuration, but we put the slot 1 at a protected level in order to diagnosticate in case of data compromission of the slot number 1. The difference also is that we know the value contained in the slot 1, and we use the slot number 9 and 10 with non-values for our attack scenario, especially the slot number 9. So this scenario is possible in the real life because if the attack is successful, you see that only having the content of the slot number 9 is needed to perform the final attack. So here is the normal execution of the read operation command. So still you have to perform the gen dig command to the ATECC to inform the ATECC that you have to it has to prepare the temporary key based on the key ID number 1, which is a slot from which is protecting the slot number 6. So then you can perform the read operation of the slot number 6. The ATECC checks if the temporary key is initialized before with the gen dig command, and if it has been done with the correct key ID associated with slot number 6. If it's the case, here yes, the value contained in the slot number 6 is given in a separate way that you can decode after that, because if you have the value of the slot number 1. In the case of the forbidden read that we will try to perturb, at the beginning we make the gen dig command on the slot number 9. So we prepare the temporary key with the KID number 9. And then with the read operation, the ATECC refused to give any value because the temporary key has not been initialized with a correct value. So it cannot compute the ciphered version of the data and return it. So it gave us an error. So here is the consumption curves of the two executions. So the first one is a forbidden read where we have an execution error, and the second one is a granted read. So we can see we have spotted the first divergence of the execution where we perform the first perturbation to get access to a granted read. So we can see also on the curve of the granted reads that two executions are very similar, and both of them have AES operation. And if we count the number of the runs, we can see that for each AES operation is done on 32 bytes. So it gives us a hint that two read operations are done by the chip, and if the read operation and decryption operation are the same at the end of the two readings, two consecutive readings, the values are is written. So it gives us a hint that we will have to make a double fault attack. So here we present back the execution flow of the forbidden read when it is perturbed. So we will perturb at the bottom right the fact that the ATECC wants to check if the generation of the temporary key is done on the correct number slots. So we assume that the last part is executed twice because the whole read process is done twice. So here is a conjunction curve we can get when we make the fault injection. So first is when there is no perturbation. The second one is when the first fault injection of laser passed. So we can see that we retrieve the first execution of the ES, but the second perturbation didn't make it. So the execution is interrupted and detected by the ATECC. On the last conjunction curve, the double fault injection is successful, and we retrieve the same pattern of the granted access. So these curves are from the 608A version, where the timing is very stable. So here is a list of several behaviors we got, because that's getting access, getting some errors. So actually, we got sometimes where we got no perturbation. Sometimes we got some random errors, and sometimes we got some data corruption. So as we have set the slot number one with a protection level on something that we can control, we have been able to diagnose which kind of data corruption we got. And what we observed on the 608A is that the data were just some bytes which are just set to 0. So it's slight data corruption. But on the 608E, the data corruption was totally wrong. So some of data corruption are problematic. The slot number 6, of course, because if your perturbation make corrupt the data that you want to retrieve, you are lost. On one execution, I did had corruption of the configuration zone, where the configuration zone was changed, and the protection level actually of the slot had been lowered. However, it was in the middle of the campaign, and when the ATECC reboots, because I continue to make some perturbation, the configuration zone is checked with the CRC at the boot up, and so I didn't manage to reproduce this attack, which will be an attack path that can be investigating, but it isn't occurred in a long time. So we got some successful attack on the both of versions of the ATECC. But the comparison of all of these behavior is this one. I would say that the ATECC version of the 608B version of the ATECC has a lot more times no perturbation due to time desynchronization and everything like this. When we have data perturbation, we can see that also that the likeliness to get some errors is also higher, a bit more higher on the version B. But the fact is that the corruption of the critical slots occurs very often, and very quickly compared to the 608A version of the ATECC. So it means that the changing to the 608B give a real improvement in terms of security of such. So this third vulnerability will say that the OneKey team sticks on using the 608A version of the ATECC even in their new products. So in conclusion, a series of design errors we have seen is first a misunderstanding of the commands of the secure device. So it's a wrong usage of the random. The second one is a misconfiguration of the ATECC by using a feature but by not knowing how to use it properly, which makes that the usage of the PIN code is totally ineffective. And the third one was vulnerability is done by a wrong plan to use a correct revision of the ATECC and don't want to upgrade to a non-deprecated version. But also we can think about the fact that we use OTP on the MCU, which is a bad design, and also to having a fixed value of the IO protect key make that there is no security patch plan to patch all the OneKey present on the field. So basically, as a takeaways, all OneKey minis before May 22, we can assume that they are all shared the same key and are instantaneously hackable. We can say also that the OneKey after this date can be attacked within 1 day, but you have to desolder the MCU and communicate them with ATC and erase the firmware. But for all of these vulnerabilities, there is no patch possible, and they need a hardware upgrade to mitigate the hardware attacks that still remains. So a little note about the communication we had with OneKey Mini. So we tried to discuss with them last year. There has been no proactive answer from them. We have presented all the description of our findings, all the recommendation, but they didn't go further. And so as we have seen here, they didn't upgrade the architecture of the OneKey, and even on the new products, they're still using the 608A version of the ATECC, and the firmware is completely similar. So the design was not modified. So using a secure component is a great idea, but you have to know how to use it. Dig into the data sheet, discuss with the vendors, because it can be very tricky to use and difficult. So if you want to embed a secure component in your product, do it properly. Thank you for your attention.
You have time for questions? Okay.
Was the alignment of the laser, did it have to be precisely aligned to some part of the chip? If so, how did you figure that out?
Actually, the alignment was very approximate, and it was not really necessary to get a very nice alignment, because thanks to the previous work of Olivier, I just had to approximately place the laser beam, so I would not be able to say what was the size of the spot, even if the positioning of the beam is important or not. Just work without any confusion.
One other thing, have you looked at any of the other secure storage devices from Atmel?
Sorry?
Have you looked at any of Atmel's other secure memories?
Not yet for the laser.
Okay, thank you.
Hi, thank you. Few quick question. Backside or frontside attack?
Sorry?
Was it a backside laser or front? Backside.
It's backside part.
Red laser, right?
It's yeah.
Okay.
It's 1064.
Yeah. Okay. Right. Another thing is that how fast was the AES? Because you did a double glitch.
I don't.
If you have that data,
I don't have the answer, but actually we don't perturb the AES execution.
No. Because you did a double glitch. I wanted to know how much was the interval between the two glitches.
It was long enough to make.
Microsecond, milliseconds. Microsecond. Okay. Thanks, Karim.
So it's not.
Finally, you mentioned some desync at some point.
Yes.
Because there's jitter, something else?
Yeah, in the 608E version of the ATECC, there is some jitter. So actually, the execution is jitter. So we managed to handle this by using a pattern detector on device.
So you said SAD.
Yeah.
Okay. Understand. Thanks a lot. Clear.
Okay. Okay, we can take one.
Hi. So you said that there was a lower success rate. There was more memory corruption on the 608B. How much more, like compared to the 608A? How many devices did you cook?
Actually, when I was running the campaign, it occurred in a few minutes, 10 minutes. So in hundreds of execution, I got some data corruption. So it was very, very, very fast. But each time, as I use an open sample, I can continue the test. Because I just corrupt the data contained in slots number 6. In this case, I can reset to a correct value and retry. It depends. So when it blocks the device, when, for instance, the configuration zone is corrupted, it happens only once and on the 608A version of the device. The thing is that in the real case, if I corrupt the value of slot number 6, it actually breaks the device in terms of the seed is
Okay. Thank you so much. Okay. Thank you.